In this section, we're going to talk about nuclear fission and fusion. So these are the bases behind nuclear power plants, nuclear bombs, the sun, different things like that. So nuclear fission and fusion. Otto Hahn and Fritz Strassmann were actually conducting experiments in the 1930s trying to create a heavy nuclei. So that's something that scientists are still working on today. So if you remember when I talked about the scientists who are creating new elements, that is really what they're trying to work on, is creating a heavy, stable nuclei. So what Hahn and Strassmann were doing was they were bombarding uranium nuclei with neutrons. So they assumed that some of the nuclei would absorb at least a couple of the neutrons, and so they would start to get bigger and bigger nuclei. So two other people who are kind of working with them here, you've got Lisa Meitner and Otto Fritsch. They actually realized that, the uranium's not actually getting bigger, it's getting smaller. It's being split into smaller elements. So thankfully, this was a small-scale experiment, because larger-scale experiment and Hiroshima would not have been the first. Hiroshima and Nagasaki would not have been the first. Anyway, in the 1940s, so about 10 years later, Enrico Fermi was actually researching fission and fusion in Chicago. So he built what's known as a nuclear pile at the University of Chicago. So a nuclear pile is actually stacks of granite and uranium blocks. Okay, so again, this is back before they really knew a whole lot about radiation and how dangerous it is. So you can see he's just kind of, standing there. Now, not necessarily as bad as, the Curies carrying around uranium in their pockets, because this does have some shielding with the graphite in there. But at the same time, it still wouldn't pass today for any kind of safety there. But these were actually used to create the first controlled nuclear fission chain reactions. So a nuclear fission chain reaction is what takes place in a nuclear bomb. And again, this was taking place in the middle of Chicago. So it's somewhat amazing that Chicago is still on the map. But this led to the start of the Manhattan Project, which did actually develop the nuclear weapon program. Okay? And again, that also took place in Chicago. And for the most part took place in the tunnels underneath Chicago until somebody had the brilliant idea that, maybe creating a nuclear weapon under Chicago is not that great of an idea. Okay? So, the stability of a nucleus depends on the nuclear forces that hold the protons and neutrons together. So we talked about the strong nuclear force and how that kind of fights against the repulsion of the positive charges next to each other. So neutrons and protons are held together by the strong nuclear force, which again only happens at short distances. Okay? So you have that inward pull of the strong nuclear force as long as you have the protons and neutrons close together. And then you also have the electric repulsion with the protons to each other. So you've got two positive charges, they don't want to be next to each other, so they're trying to force each other apart. Okay? So when the electric repulsion becomes greater than the strong nuclear force, that's when you get nuclear decay. Okay, that's when something gets forced out of the nucleus, okay, because of those like charges repelling. Okay, so in a stable nucleus, the attractive forces, the strong nuclear forces, are stronger than the repulsion forces. But if you get too many neutrons or protons shoved into a nucleus together, okay, you can actually destabilize that nucleus. Okay, and once it's destabilized, once it's unstable, it will start to decay. Okay, now it might seem a little weird that the neutrons can do that as well, but really just getting a nucleus that's too big can completely unstabilize it because it's too big to be held together by those short distance strong nuclear forces. So neutrons can help to hold a nucleus together, okay, but again, there is a limit to how many neutrons a nucleus can hold. And once it hits that, there's not a whole lot of help that can be made, okay? So too many or too few neutrons can cause a nucleus to be unstable. So nuclei with more than 83 protons are always going to be unstable, right? They're always going to be radioactive. And then radioactive decay, usually several rounds of it, will actually result in a more stable nucleus. So that's kind of the goal of all of this radioactive decay. So when we start talking about nuclear fusion, okay, this is when you have two light nuclei combined to form a heavier nuclei. Okay, it's also going to release a lot of energy in the process. So this is actually what takes place in stars or in the sun. So in stars, you have hydrogen nuclei combining to form helium. So you have two protons, maybe some neutrons in there, basically being forced together to form a helium. So they hit with enough speed, enough energy, because of all the heat that's contained in the sun, that they will actually fuse their nuclei together. And then once you have those two protons in there, you have an element of helium. So that releases tremendous amounts of energy. Okay? Now, that's good that it keeps releasing all of that energy because energy is required to bring those hydrogen nuclei close enough together for that to occur. Okay? So once a star gets started with this nuclear fusion, it doesn't really stop until it runs out of hydrogen. Okay? Or when it starts getting really low in hydrogen concentration. There is actually a point where it will start to slow down. Okay, so humans have actually been working on trying to make fusion a reliable energy source on Earth. It hasn't really worked out too well as of yet, simply because of the amount of energy needed to start it off. And usually that energy is in the form of heat. Okay, now we can't really contain something that's that hot, okay, that size and that hot. So scientists have been working on what's known as cold fusion, okay, where you don't actually have to have that heat, but it's relatively tricky in trying to get that to work, okay. So that energy required to bring the hydrogen nuclei close enough for this to occur, okay, for them to fuse to form a helium, is accomplished by those high temperatures in stars. So in the sun, that actually happens in 3 stages. So first up, you're going to have 2 hydrogen atoms fusing, okay? So you have a proton and a proton, both of them are 1 and 1, and then you end up with 2 over 1H, okay? So there's a neutron involved in there as well. And then again, you have another hydrogen fusing with hydrogen, okay? And you end up with helium for the first time, and you're also releasing gamma radiation. Okay, now this helium has 2 protons, 1 neutron. Okay, but eventually it wants to get up to 4 total. Okay, so 2 neutrons, 2 protons. So 2 of these 3 helium-3 atoms are going to fuse together on their own again to become a helium-4 atom. Okay, now this is also going to release 2 hydrogen atoms, okay, which goes back to the beginning and keeps going. Okay, so eventually you will run out of hydrogen because you're using 3 of these hydrogen molecules to form one of the heliums. Okay, and then you only get 2 back. So eventually you will run out of hydrogen. You're also building up your stores of helium. Okay, so this is kind of depicting what this looks like. You have your 2 protons, your hydrogen nuclei coming together going to release other little things and get one H2 molecule, one H2 atom coming out. Then you're going to react it again with another hydrogen, okay, so another hydrogen nuclei. You're going to get your He3 molecule, 2 protons, 1 neutron. Okay, react 2 of those together, and you're going to get your helium-4 molecule out, as well as 2 of your hydrogens back. Okay, so you can see how this can kind of cascade pretty quickly. If you're producing these hydrogens back out, they can go on and kind of kickstart the next reaction and continuously keep going with this. Nuclear fission, on the other hand, is not so much about fusing 2 nuclei together as it is about splitting them in half. So this was a whole big, huge deal back in like the 80s, 70s, 80s about splitting an atom. They didn't think it could be done. They didn't think that, you know, we could have enough energy to actually split the atom. And then when they did, you know, things happened. Okay, that was World War II, the end of World War II. So nuclear fission is the process of splitting a heavier nuclei into 2 or more lighter nuclei. Okay, so this is usually achieved by hitting a large nucleus with a neutron. Okay, so this is where that neutron decay comes in and why it's such a big deal. In the fission process, when the nucleus splits, you're going to get neutrons released, so extra neutrons, which can then go on and hit more atoms and produce more of these reactions. You're also going to get a large amount of energy released. So if you have enough of these neutrons hitting enough large nuclei at once, you're releasing a whole massive amount of energy. Okay? And if this reaction is not controlled, right, that amount of energy creates the nuclear explosion. Okay? So, note, in these reactions, you're going to have to account for all protons, neutrons, and charges, okay, in order to keep the reaction balanced. Because again, remember, you can't create energy and you can't create matter. You can't destroy them either. Okay, so all of that has to be accounted for. Now, we're not going to focus too much on the energy in these. We're just going to focus on the matter side of things. Okay. So this might look confusing, okay, but looking at this, we have, let me get my laser pointer. Okay, so we have an atom of uranium-235, okay, radioactive atom, often used in nuclear fission reactions. You hit it with a neutron. Seems like a simple thing, but you're going to split that uranium atom, okay? And you're going to split it into an atom of barium-140 and an atom of krypton-93, as well as 3 neutrons, okay? And you're also going to release energy, all right? Now, like we did in the previous section, you need to add up everything on top and everything on bottom and make sure that both sides of the equation are equaled, okay? This is a depiction of what this would look like. So you have your uranium-235 here. You're going to hit it with a neutron, and then that's going to split into 2 smaller nuclei. Okay? You're also going to get more neutrons released. Okay, so they can go on to hit other giant atoms. Okay? So this is only one of the ways in which uranium-235 can decay. If it's hit in a slightly different way, slightly different area, it can split into multiple different combinations of elements. So we are going to stop here and continue looking on this in the next video.